Hi, everybody, and welcome to today's roundtable discussion, which is going to focus on reducing pollution and cost with energy storage at tribal businesses. This is the third and final roundtable in the TribalP2Action online event series. There's another webinar occurring next week, but we're excited to have you join us here today and looking forward to discussing this, I think, very timely and important topic. I want to step back for a moment and give an overview of the TribalP2Action project, and I apologize for all those who have seen this several times that have continued to participate. But the Intertribal Pollution Prevention Project is an EPA grant-funded project. It was a grant received by the Paula Band of Mission Indians who are administering it, and it's a collaboration between Paula, the San Pasqual Tribe, the US EPA, Prosper Sustainably, Microgrid Institute, Wood Environmental, California Green Business Network, among others. The project has two major components. The first is the local P2 assessments and planning that's focused on Paula and San Pasqual businesses. So there are, I believe, 8 or so Paula businesses that we've been focusing on here on your screen, including the casino resort, some agricultural groves, the Fox Raceway, gas station, RV resorts, their gas station and mini mart, transfer station, leak department, and wastewater treatment plant, and then San Pasqual's Woods Valley Golf Club. That same component also involves employee training and green teams to build awareness among employees and stakeholders that are working for these businesses. And this TribalP2Action project is part of the national component of this grant program. And so this is what we're calling, this is a training capacity building program, and you can visit TribalP2Action.org to find more. And as I mentioned, this is part of an 8-part series with 5 webinars and 3 roundtable discussions. This is the third of the 3 roundtable discussions, and the 5th webinar is going to be held on Tuesday next week. All of the webinars are being recorded, and most of them so far have been posted online. I believe the only thing that hasn't been posted so far is webinar number 4, which will be posted, if not by the end of this week, then next week. And we may actually post some of the roundtable discussions if we find that there is no sensitive content. We want these roundtable discussions to be a place you feel free to discuss your challenges, and if we feel as if there isn't any sensitive content, we will first seek everybody's permission to post it. But we want this to be a free-flowing discussion where we can kind of, talk through these things. All right, so I'll kick off introductions by introducing Shasta, who I don't believe is here today. Shasta's birthday, and I think she had to attend actually another event. But Shasta is the Environmental Director and Tribal Historic Preservation Officer for the Paula Band of Mission Indians. She's been overseeing this whole project, and we miss her and her screaming goat, who typically is there to bring our attention to the screen, to answer polls and other questions. But we'll be talking about various projects that we're working on with Shasta throughout this presentation. Jessica?
Thanks, Josh. Good morning, everyone. My name is Jessica Counts-Arnold, and I am the Pollution Prevention Coordinator at EPA Region 9. I'm also the project officer on this grant, and I really appreciate Paula and partners sponsoring these webinars and roundtables for you guys. I believe P2 is really the key to sustainability. So thank you, Josh.
Thank you, Jessica. And I saw your note, Michael, and perhaps, instead of saying, we'll review for, if you do not want us to post this recording, please let us know, and we will not have this one held. As Michael mentioned, it may be the better route to go, as opposed to waiting when people aren't necessarily that concerned about it. All right, so I'm Josh Simmons. I am president and founder of Prosper Sustainably, which I started in 2014, primarily to serve tribes in the areas of energy, sustainability, resilience, and climate adaptation. Prior to Prosper Sustainably is the lead consulting group on this project, and prior to starting Prosper Sustainably, I was the environmental director for the San Ynez Band of Chumash Indians, which is located in Santa Barbara County, California. Michael?
Hi, I'm Michael Burr, the director of Microgrid Institute and also a principal consultant for Burr Energy LLC, which is a consulting firm. And we work closely with communities and tribes and a lot of other clients, focusing mostly on energy resiliency and sustainability. Have had the pleasure to work with Josh at Prosper Sustainably, as well as the Paula Band and San Pasqual Band and some other tribes for several years now, looking in particular at microgrids, but also at other energy sustainability initiatives. So glad to be here today for this really interesting roundtable.
Thank you, Michael. And I realize I skipped over you, John. I apologize. So John Flores. John, you're still on.
Can you hear me?
There you go. Yep.
Can you hear me now? All right. Hey, Josh. My name is John Flores. I'm the Environmental Director and Water Manager for the San Pasqual Band of Indians. I've had the pleasure of knowing Josh for quite a few years and working with him on a few different projects these last few years, and also working with Shasta at Paula.
Thanks, John. And then one of our special guests today, Rob Brown from Invinity Energy Systems. Rob, can you introduce yourself?
Absolutely. Thanks, Josh. So this is Rob Brown, Director of Sales for North America for Invinity Energy Systems. We at Invinity Energy Systems do vanadium redox flow batteries. We're an equipment manufacturer and the first company in the world to bring flow batteries to be a product as opposed to a project. Built from two companies, Avalon Battery and Red T Energy, merged together in April of this year to create what is now Invinity Energy Systems, to essentially be the foremost flow battery provider of the world, with about 80 employees and about 10 to 15 megawatt hours of installed capacity worldwide. Good to be here.
Thank you so much, Rob. We really appreciate you joining on such short notice. And as we'll talk about a little later, we're collaborating with Rob on a tribal microgrid project. I want to also just give a quick shout out to Scott Brown, who was unable to join us today. They have been supporting the TribalP2Action project, focusing on hazardous substances and water use and conservation. And they've actually led the webinars and roundtable discussions on those topics, which have occurred in the prior 2 weeks. And you can go back and view those at TribalP2Action.org. And Scott always likes to point out Wood Environmental was formerly AMEC. And so, yeah, thank you everybody for joining us today. We're excited about this discussion, and particularly, in California, this is a very timely topic with the shutdowns that have been occurring, energy shutdowns that have been occurring throughout the state due to the wildfires. We're going to kind of rehash what we've rehashed for every single event, just to ensure that you understand the terminology that we're using, what pollution prevention is. Pollution prevention is any practice that reduces, eliminates, or prevents pollution at its source. It can also, I would say, be thought of as environmental sustainability or greening. So we're really talking about greening businesses or other organizations. And the hierarchy here is on the right. You really want to be reducing pollution at its source before then you proceed to reuse, recycling, treatment, or disposal or release. And you can go to the EPA's website to learn more about the EPA's pollution prevention program and the funding and technical assistance and other resources they have available for tribes and other communities. And then to put energy in the context of pollution prevention, we have some additional resources, and I have there's kind of a similar but different hierarchy. You first, in the energy space, want to focus on energy conservation, then proceeding to energy efficiency. After that, you want to then bring in renewable energy generation. To the extent that you can't offset fossil fuels with renewables, then you want to try to use lower emissions fuels sources. And then as a last resort, we'll be using the conventional fossil fuel energy sources. EPA has its Energy Star program. It focuses on energy. There's also at the end, we have some resources for energy, specifically energy storage, and EPA actually does have a web page focusing on energy storage as well. And then for tribes in particular, one of the greatest resources is going to be the Department of Energy Office of Indian Energy policies and programs, and they have free technical assistance and annual funding cycles for tribal energy projects, including for energy storage in microgrid systems. So I'm going to pass it over to Michael Burr right now to kind of get us kicked off into the depth of the content. And but we want to encourage you to add to the conversation, ask questions throughout. We're definitely going to make this more of a dialogue than just a presentation.
Great, thanks, Josh. Just wanted to quickly kind of get on the same page with some terms. There's an awful lot of acronyms and technical terms in the energy business generally, and a few of them we'll talk about and refer to today. Just basically when we talk about an ESS, or you see that acronym, that just stands for Energy Storage System. Simply put, captures energy for later reuse. BESS, or BESS, is a battery energy storage system. Not all energy storage systems are batteries. So then DER is a common term in use these days, distributed energy resource. Mostly people talk about distributed generation, small generation systems that are distributed throughout the electric grid, whether that's behind the customer meter or in front of it on the utility grid. But distributed energy resources also refer to controllable loads. A battery is both. A battery is both a energy source when it's charged up, and it's also an energy load when you are charging it. So there are other types of DERs that are just controllable loads as well. But anyway, DERs are both. So then finally, when we talk about a microgrid, I usually kind of shorthand this to say that it's a backup power system on steroids, a complex backup power system to serve multiple facilities, many different loads, and to manage those loads normally usually to manage those loads in an intelligent way with some kind of control system. The definition that's provided here, I believe, is the DOE's definition, which is fair. There are, however, microgrids that don't necessarily fit that definition if they're entirely off-grid. So not all microgrids are actually interconnected to a grid. So that's, I think, all we need to say about that for now. I would mention that, you'll hear the term nanogrid, you'll hear the term solar plus storage system and backup power system. You can argue they're all microgrids. A nanogrid is just a very tiny microgrid, generally serving one building. A lot of times that's just boiled down to a solar plus storage system where you combine a solar generation system with a battery. So that's, I think, probably enough on the terminology. Josh, do you want to move ahead to the next slide? I think you're.
I want to pause here and come back to what Sherry was talking about and their consideration of a microgrid for their community in Maine. And so, Sherry, when you talked about, I believe that was Sherry, you mentioned that, right?
Yeah. It was Sherry.
I guess, can you share a bit more about what you're considering and what's part of that inclusion, how you're defining a microgrid, just so we can kind of frame our discussion?
Oh boy. Well, it would be, we're looking at solar generation, and we're looking to support our community and tribal offices and tribal businesses.
Okay, so is it a microgrid typically, a microgrid includes the ability to be disconnected from the grid, either temporarily or permanently. So is your solar PV system supposed to have the ability to operate off of the grid, or is it, I guess, or are you just kind of talking about a community solar farm or community solar system?
I think currently we're looking at doing the latter because there's opportunity to sell the excess energy. That's so I should have mentioned that. I think that's an option that we're exploring.
Yeah, and I think, and we'll kind of talk through, I think, as we get a little further along. I just wanted to, I think there's considerations of, there's costs to adding so what you're talking about, we would term as community solar rather than a microgrid. But, I think for your analysis right now, you want to consider, does a microgrid make sense, or does storage make sense for you, both for resilience purposes in terms of being able to have backup capabilities, And also from an economic standpoint too, in your ongoing operations, solar may allow you to reduce, storage paired with solar may allow you to reduce some of your costs depending on what the capital investment is. So we'll kind of keep that in mind and come back to you and probably circle back with you and talk it through a little bit, but we'll kind of keep that in mind as we're framing our discussion. So thank you.
Sounds good. Thank you.
So we're going to start with a little bit of a case study, just to kind of put some, it can be hard to talk about these concepts without actually seeing them and thinking them through a little bit, particularly if they're new for you. So one initial question is why energy storage? And there's a lot of reasons that we'll go through, at least the primary reasons behind why you'd want to consider an energy storage system. But we're working with San Pasquale right now in installing a microgrid system for their tribal government complex that includes energy storage. And the main purpose there is well, actually, John, let me hand it over to you, and you can kind of share the drivers behind this project that are leading to our work together.
Hi, everyone. Yeah, so we've been working on a microgrid system here at San Pasquale to service our government complex. Our government complex includes our tribal administration building, our housing department, there you go, there's a map of it right there. So number one where you see, that's our tribal admin building and tribal hall. Then the next building between 2 and 3, that's our housing department building and police department. Down where number 4 is, that's our fire department. And then where you see 5, 6, and 7, that's our educational area down below. Our tribal hall is also a Red Cross emergency evacuation shelter, and we can also use our education building for an evacuation shelter as well. And you can see where we have a parking lot up above, that's our employee parking. We're going to do some solar canopy parking, and the microgrid is going to go, the actually battery storage will go down where number 3 is, and we're going to have some backup redundancy with the liquid propane backup generators. As you can see with these fires going on in California right now, in San Diego, and throughout the West, solar is great when you have sun, but then obviously when we've had so much cover from the smoke right now, obviously we want to have full recharge on the solar, so that's where the backup generators will come in. But why do we want this is, we experience a lot of blackouts here, rolling blackouts out here in San Pasquale, whether that's due to high winds, fire events like we're having more, someone hitting a utility pole and the power just going out, infrastructure upgrades. SDG&E is doing a wood to steel pole conversion project, so they're constantly taking the grid down to install new poles or new infrastructure. And so, we were tired of all of these affecting our tribal admin building. We don't have any backup generators, diesel generators, and instead of using 20th century technology, we decided to go with a 21st century technology solution for all these issues we've been having. And the main benefit is always going to be we'll be able to island off the grid during a power outage event and keep power going to all those buildings. But we're also going to see a lot of, there's a financial reason as well. We're going to see a lot of savings each year on our energy bill going forward. And we're also going to be able to put in some EV charging stations in the parking lots there. So we're trying to do outreach and education to get maybe move our cars, our fleet, our government fleet to electric vehicles so we can charge off of this, and also to promote it within the community. If people want to start buying electric vehicles, they'll have a place to plug in and charge. So there's a lot of benefits. It's not just one. It touches on basically everything the tribe wants, savings on energy bill, emergency power during an emergency situation, and then the EV chargers as well. So yeah, it's going to be a great project. We're also going to be down in the corner. You can see we're also adding a 3-phase component because we've been growing so much, and we needed, we're kind of outgrowing our grid anyways that we have with single phase. So we're upgrading to 3-phase, which will allow for future expansion of the government center. So yeah, San Pasquale is a growing tribal government, and this is going to meet our needs going forward in the 21st century for the tribe.
Yeah, and thank you, John. And this is, an exciting, awesome, complex project. It's involving this many facilities, these types of systems. I think we're going to start seeing more and more of this, but I would still say this is kind of cutting edge in terms of its complexity, integrating new solar with existing solar, and integrating the EV chargers along with the lithium-ion storage and the backup generator. We're kind of going back to what John was talking about. In California, there are regularly now public safety power shutoffs in areas that are called high fire threat districts, and San Pasquale is getting the power shut off for a day or more on a fairly regular basis, so pretty much an annual basis now, and losing power during other events, severe storms. Now we're seeing, I think in the wet season, more shorter bursts, more significant storms that are leading to flooding and mudslides, and so, the community, I think the primary driver was the resilience for this project, and then the economic benefits were shortly behind that. This is partially funded by a DOE grant through the Tribal Energy Program, the one I mentioned before, as well as a grant through the Grid Alternatives. And so, this is being subsidized by those. I think for tribal energy projects, those are you want to be looking at that every single year to fund these types of projects. You usually can get up to $2 million pretty regularly now for these types of systems. So just to kind of, before we go into a little more depth, explain some of the cost savings concepts. The cost savings are coming in two primary areas. One is certainly you're adding solar here, but we're talking about storage. Solar is going to potentially and likely be more cost effective than the grid supplied power. But the energy storage allows you to store the solar that's produced during off-peak times, and then use that solar, deploy it to the facilities during the on-peak times when the prices of the energy are higher. So this is called time of use energy arbitrage. And you can do it with solar, but you also can do it by charging the batteries during the off-peak period. So the meter is running, you're paying the utility, in this case, San Diego Gas and Electric, during the off-peak times for off-peak pricing. And this is just example purposes. These aren't actual figures. I don't know what their exact rate schedules are right now. But you charge it during these 33-cent per kilowatt hour periods, and then you use that energy during these on-peak periods where you're paying possibly 20 cents per kilowatt hour more or watt hour. And that's where you're going to achieve those energy savings. So whether it's off-peak energy or whether it's solar energy being generated during off-peak periods, you want to be pulling energy from the grid as little as possible during this period of time. So that's kind of one of the two major areas where you're going to receive cost savings. The other area is what's called peak shaving. So there's two aspects of an energy bill, at least on a commercial energy bill, and the time at which you use energy, the cost can change throughout the day. The on-peak times, the reason they're so expensive is because that's when the demand is the highest. At the same time, that's also when the utility has to bring on more capacity. They bring on what are called peaker plants. In California, they have natural gas peaker plants that fire just during these times to meet the increased demand, which actually mean that this energy is dirtier during that times as well than it is during off-peak times when you actually have predominantly renewables available. And so, by displacing this, you're not only saving money, you're actually reducing the environmental impact of your energy usage as well. So that's still kind of the first area of savings. The second area is called peak shaving. The other aspect of your energy bill is how much you use in energy at any given moment. Think of it as like the size of the pipeline. So, you turn your HVAC system on and all of a sudden you have a huge draw from the grid, and the grid needs to have the capacity to give you all the energy you need in that instant. And that means that the grid needs to actually have the infrastructure installed to meet that peak demand. And the utilities charge you based on any peak you meet over a given period of time or a given month, typically a monthly cycle. And so by installing battery storage, instead of having those spikes hit the grid, you can have that energy be pulled from your battery which will mean that peak charge will not hit the grid. It'll be lower. You'll pay less money over time. A lot of the projects we're working on, the demand charges, that peak shaving, that overall cost before the installation of these systems is sometimes as much as the use of energy. So, you could have $1 million energy bill, and $500,000 of it is for the actual energy you use, and $500,000 of it is for how much you use, the peak amount of energy you use in a given month. So it's a bit of a complex topic. I probably didn't simplify it that well, but those are the two primary areas where you're going to save money through the use of energy storage. So I'll turn it back over to you, Michael, and perhaps you can succinctly in a sentence describe each of those if you feel like it's still necessary.
Sure. And we'll get a little bit more into the particular attributes of different types of energy storage in a minute. But overall, just kind of recapping what Josh was just saying is that there are benefits of energy storage in terms of the ability to displace dirtier power. That's really the main thing. And that comes in two forms, as you see in the bullets here under the environmental header. First, you can store renewable energy and use it later. There are many systems where, if you are generating more power than you can use, either you have to curtail that or you have to sell it to the grid. And sometimes you can't export it to the grid, and so it just gets wasted. A battery system would allow you to store that, or I'm sorry, not a battery system, a storage system, because there's, as I mentioned, not all storage systems are batteries. But anyway, the ability to shift when you actually use that renewable energy is, creates a substantial environmental benefit over just wasting that energy, or for that matter, pushing it onto the grid. Because if you push it onto the grid, then it's going to go up into the system and be distributed, and there's going to be loss in that system that may be less than the loss from storing it in your battery. So it's not a free storage system to just push your power onto the grid. So as Josh, I think, pretty clearly went through, the other thing is displacing dirtier power. So during peak periods, that's the dirtiest power you're going to be using from the grid. So if you can reduce the amount that you use, that's going to produce a pollution prevention benefit. And storage can do that as well as other things that you can do for demand response or just using cleaner power. And then finally, this is something that tends to be overlooked. The use of stored power, is cleaner than using diesel-fired power, for example, during an outage. So if you're in a situation where you do have a lot of outages and you're using quite a bit of backup power, this can add up pretty substantially, because those little diesel-fired or even LP or gas-fired generators are nowhere near as clean as, certainly a solar system obviously is 100% clean, but nowhere near as clean as even the grid. So if you can displace the use of or reduce the amount of backup generation that you have to rely on with a battery system that's storing cleaner power, that's a pollution prevention benefit. And I think Josh pretty much went through the economic benefits for the most part. But I did want to point out grid services. Like, there are things that batteries can do to actually support the utility grid. And the owner can get compensated for that in some situations. Not all, but those are certainly benefits that do stack up when you're looking to try and figure out, what's the economic cost-benefit analysis on a given investment. I think that's about all I had to say. Anything else you wanted to add, Josh?
Just related to that, it's just, the grid services, the reason they're willing to pay for it is because the IOUs have to basically invest in that additional capacity that is not used on a regular basis, and they prefer not to. So, you have both a potential cost savings benefit, but also an environmental impact. I mean, if they don't have to install as big of transformers or power plants or other facilities to support local energy needs as a result of these local energy resources being available, then you're both saving money and reducing your environmental impact.
Hey Josh, this is John. Can I just comment on that a little bit there?
Sure.
On the other, I would add, and this is one thing I'm always big on, and I think others will agree on the line, is tribal sovereignty. And when a tribe is able to produce its own energy and store its own energy, they are increasing their sovereignty in the energy field. So I think it's the first step that some people often overlook is when the tribe can obviously produce its energy, whether it's through solar or wind, you know, because we're not blessed with anything like oil or any, you know, the old fossil fuels on our reservation to mine for energy. You're able to increase your sovereignty and decrease your dependence upon, you know, these IOUs, and maybe one day, you know, go completely sovereign and be your own energy producer and store and can create all your energy for your tribal needs on your land.
Yeah, that's an important point that I should have put on there and had on other I think maybe even our presentation on Tuesday. So thank you for pointing that out, John.
Can I just add something to that, Josh? Like, this really goes to Sherry's point, or Sherry's question, about, you know, the benefits and pros and cons of installing just a solar system versus a microgrid and using storage. If you have a solar system, but it's not located within the boundary of your energy domain, or in your, you know, behind the meter, basically, or within the area that it's being used, then it's going to be really hard to utilize that solar to actually achieve greater self-sufficiency and sovereignty. Because during an outage, if you don't have that solar system integrated into a microgrid that is serving the customers with that power directly, then really that system is just an economic exercise. Your solar system is just, in effect, displacing on your bill what the power is, but it's not actually providing the electrons to your loads. So it's important to distinguish between a remote net metered community solar system versus one that's actually within the community and actually serving those loads directly.
Yeah, and I guess I'll also add too, because I don't think we really brought it up before, is normally a solar PV system, when the grid, if it's grid connected, when the grid goes down, that solar PV has to shut off. Because if it doesn't, it's going to backfeed. If it's overproducing, it's going to backfeed energy into the grid, and it's going to kill people. I mean, that's a huge health and safety risk to electrical line workers. If you have it paired with storage, then you can have it where, and it typically is set up where the solar remains online. So you continue to benefit from having the solar energy being available. So not only do you have during an outage, do you have the energy that was stored in the battery at the time of the outage, but if you have a renewable energy system tied to it, then you also have a continuous source of energy generation until the power is restored, that is continuing to supply the loads, but also displacing additional fossil fuels that you may be using if you also have backup generators on standby waiting for when the batteries run out. Let's pause here just for a moment. I want to see if there's any questions. If anyone wants to raise their hand or speak up, you know, ask any questions before we talk about the different storage technology types. And I think, you know, Michael, we had Sherry had one point, and somebody else had raised something about some systems that they were considering, and it's just I start speaking too much and drink too much caffeine. I can't recall exactly what else was asked about.
Yeah,
so I want to make sure
water pumping. Yeah, we'll talk about that.
Okay. Well, feel free to jump in, you know, either put in the chat box or feel free to unmute yourself if you want us to come back to this. Otherwise, we're going to move on to comparing the different types of storage technologies. Go ahead, Michael.
Sorry, I was just fighting with Zoom here for a second. Yeah, so I'm just going to very briefly and at a very high level talk through some of the most common energy storage technologies. This is not a comprehensive list. There are different flavors of each, and there are things that are continuing in development. So don't take this to be the Bible on energy storage by any means. We're just trying to cover the high level. So the oldest, or you know, I guess one of probably the oldest form of electricity storage is lead-acid batteries. I'm not an expert on this, so there may be some other variation that came before it, but they've been around a long, long time. So in fact, some of the first cars were electric cars using lead-acid batteries. So that's a very solid, well-understood technology. The problem is there isn't a lot of energy density. Actually, I'm not going to get into the pros and cons here. We'll get into that in a couple of slides here, but basically that's an older school technology. Lithium batteries, everybody's aware of, and they carry it around in their pocket and a cell phone all the time. That's the more common market leading really technology for a lot of energy storage applications today. And it's got higher energy density than lead acid, which means it's just weighs a whole lot less for the same amount of capacity. There are some downsides to lithium that we'll talk about. Flow batteries, we have an expert on that who's going to talk further about that today. And Josh will turn it over to him in a second here. But also there's flywheel energy storage, which is something that's, a lot of people might think that seems like an odd approach to energy storage. But in fact, it's become really pretty sophisticated and fairly cost effective. So it's just wheels, a lot of big, heavy wheels that you get spinning, and they stay spinning as long as, there's no drag on them. And if you put enough of them together, you can have very reliable, fast energy storage, fast reacting energy storage. That's pretty interesting. Those are those first four ones I want to point out, and in this slide that we'll see, they're highlighted in red because they're the ones that are commercially available, modular systems you can kind of adapt for your purposes. Hydrogen energy storage is something that, we've seen out there that has been, people have been working on for a long time, and it seems to be like 20 years away forever. And hopefully someday we'll get there. Basically, the idea here is to use electricity to split water, to use electrolysis. You run it through water and it splits into hydrogen and oxygen, and then you separate those two gases, and now you've got hydrogen, which is, a super dense source of energy. That's the basis for all of our fossil fuels, is hydrogen. That's why it is, a dense energy source. So you compress that and you can store it for long periods of time, but so far that has not really become a really commercially viable system, but it's getting there. So compressed air energy storage and pumped hydro storage are similar in some ways. These are mechanical systems that compress or they put a fluid somewhere that it can then later be extracted. So in compressed or air energy storage, normally what those systems are is large underground salt caverns or things like that, that air is pumped into, and they can apparently hold a huge amount of air and pressure, and then that pressure can be relieved through a turbine when you need that power to come back. And then pumped storage, similarly, most of, the biggest, in fact, most of the energy storage capacity in the world is pumped storage. These are grid scale, very large systems, mostly using huge reservoirs. So you've got a big reservoir, and it's a matter of pumping water uphill, and then when you need it, letting it flow downhill through a turbine, just like a hydropower system. So those two systems are very much dependent on location. So, except now there are some companies that are trying to produce small scale modular compressed air energy storage systems, but that's another thing that's been kind of 20 years away forever. It's hard to make those systems really cost effective. And there's no Moore's law upside in terms of development when you talk about development of semiconductors and battery systems that have very, very small scale, molecular scale development that's happening. There's potential for real improvements in batteries and in some other forms of storage that are like semiconductor based, supercapacitors, in particular ultracapacitors. Those things will continue to get better and more cost effective, but compressed air energy storage and pump storage never will, because those are basic systems based on mechanics. And then thermal energy storage in a similar situation. We'll talk about some specific cases there. Those are really pretty interesting. Some of them can be used to produce electricity, but some can't. So maybe we can move on the slide, move to the next slide now, Josh.
Okay, yeah, and but some thermal energy storage is just a huge ice box that you release and then offsets your thermal loads for heating and cooling. I actually want to pause here for a moment and come back. I think it was Tabby who talked about the hydro that they were considering or utilizing in their community, and was it Tabby, Michael? Do you have in your notes?
Yeah, that's right. So I guess did you want to say something specific? I had some thoughts on that. Go ahead.
I want to learn more from Tabby first to just, give more context of what they have going on or what they're considering. And then I think we could maybe speak to it after that. Tabby, are you still available to share a bit more about your situation?
The idea, I think it was just an opportunity that one of our energy managers identified. We have a tribally owned corporation, so we're an independent power producer, but we sell that offsite. And so we were trying to think of ways that we can have locally produced power that we use here locally. And so we have big dams like located throughout the reservation. And so we wondered if we could do some sort of local systems using pumped energy there. And we're going to have to rebuild some of them anyway, or update some of them. So we thought it might be an opportunity to work on that.
Yeah, I mean, I would definitely think, certainly it's going to be a case-by-case thing that needs to be studied to see, what the potential is there for how much you're pumping into the reservoirs, how big they are, how much you're releasing at certain times, and whether that actually aligns with your energy use patterns. The only thing I'm going to share, Michael may probably add a bit more, is just some resources you can utilize to study that. The BIA has their Energy and Minerals Development Program has a typically annual grant for studying these types of opportunities, and I don't believe there's a specific match requirement there. Sometimes the DOE has funding available to study these types of things, but I haven't seen money for planning or studies in actually several years now. But at the same time, DOE and the BIA both offer free technical assistance. So you could have the DOE have people from the NREL or other areas. They even hire subcontractors that will actually study it on your behalf. And, just to understand the viability of that. In addition, looking at, talking to universities and other institutions that may be interested in studying and working with you as a student project or another project as well could be a good option. Michael, anything to also add or share?
Yeah, just the one point. There are many different forms or flavors of pumped storage. You can call a lot of things pumped storage. I guess I wanted to point out one thing. When we're talking about large reservoirs, what the one pitfall to look out for is the environmental permitting on any changes related to open reservoirs or rivers or anything like that can become very onerous really quickly. The Federal Energy Regulatory Commission has a hydropower division that does nothing but review hydro licenses, and pump storage is one of those things. The pump storage systems that seem to be easiest to get done are the ones that use an existing reservoir. So if you've got existing reservoirs, you're already a big step ahead. But the other thing is closed loop systems. If it's a big open reservoir where there's wildlife that's using it, it's going to invoke hydro licensing requirements that can be real costly, time-consuming, and onerous, depending on the system. Closed loop systems use tanks of one sort or another, or at least like a water system where it's not wildlife using the water reservoir. In those systems, you can have better luck. You can use, in-pipe generation systems. So those are just a couple of thoughts to add. I wanted to mention, too, as a general matter, why I had misheard what she was saying before. I thought she was talking about water pumping for irrigation or other purposes. We see some really, really interesting applications of microgrids or just, off-grid solar systems for water pumping. If you do a lot of water pumping and if you have some storage of that water, then you can use solar to pump it when the sun is available. And so those are some interesting things to look at. It's not energy storage exactly, but it's using some of the same principles.
Well, I think, an energy storage consideration to the extent that it's not going to have environmental impacts. If you have two different reservoirs that you can pump water back and forth to, you use that renewable energy source such as solar or off-peak power to pump it to the reservoir. And then, depending on your round-trip efficiency losses, you could re-release it. And when you need it, when energy is more costly, and you could possibly save money that way as well. So, but I think it's definitely because there are free grants and free technical assistance, and it sounds like, I would encourage you to reach out to both the BIA and the DOE about getting some technical assistance to study this. And a lot of times when you kind of get in the queue to run these analyses, that way that you usually will set yourself up better for getting funding, either for further studies or possibly for implementation. This would definitely, an actual implementation project would fall under the realm of the DOE Tribal Energy Program grant as well. Tavi, does that help you? Have any additional questions or context?
Yeah, that was helpful. I think good starting point. We're kind of at the very beginning of the conversation, so good things to think about. Thanks.
Great. Thanks for sharing. Michael,
Okay,
I'll hand it back to you.
Pick it up? Yeah. So I just kind of alluded to the fact before that some of those variations I mentioned are, off commercially available systems. A lot of systems now are being packaged and being offered for sale. Some are not. There's a lot of technologies that are in more development phases. So these pictures here depict mostly lithium batteries, but also lead acid batteries that are packaged in different forms. A lot of people are familiar with the Tesla Powerwall, which is depicted there. That's mostly for residential use, but for bigger scale commercial use, Tesla has other systems, but a lot of other manufacturers are out there that are selling lithium ion and lead acid batteries in particular, but also now flow batteries, which we'll get into in a minute with Rob's additions. So I think you can move ahead to the next slide there, Josh. So just wanted to point out a few things to, in particular, think about with regard when you're evaluating different energy storage possible options, what the factors are to consider for pollution prevention purposes. So first of all, it's just a matter of capacity, but there's two types of capacity when we talk about energy storage: power and energy. So you might think they're the same thing, not quite. Power is instantaneous. It's the amount of work that can be done like right now at a given time. Energy is a duration that work can get done. So you could have a 100 kilowatt battery that can put out 100 kilowatts instantaneously, but maybe it can only do it for 15 minutes. So that's a 25 kilowatt hour battery. Just a really easy way to think about it. It's 100 kilowatts. And if it's only 15 minutes, that's a quarter of an hour. So a quarter of 100 is 25. So then the other factor is round trip efficiency. So different energy storage systems have different levels of efficiency, and also within a battery type, depending on how it's designed and how it's managed, even a given like lithium batteries can have a wide range of efficiencies. But generally, lithium batteries are pretty efficient, considered about 90% in that neighborhood. We'll get into, and when we show the next slide, there's a table comparing things. But there's a wide range. There's some energy storage systems that are more like 40 or 50% efficient. You're probably not going to prevent pollution if you're losing half of the energy you're storing. So, keep that in mind. Efficiency is really important from a perspective of pollution prevention. And then finally, not finally, I guess, but related to end of life as well is environmental hazards of the battery or the energy storage system itself. So lithium batteries, we've all heard about, accidents happening, fires being caused, and batteries literally blowing up. You probably know somebody who's had that happen. So lithium can be pretty dangerous. And so that's a risk. But also the lithium electrolyte itself is an acid. It's toxic. And that's true for most battery systems to some degree, but it's a matter of degree. And, maybe Rob can talk about the risks of the flow battery system versus lithium batteries. But also other types of storage. We talked about flywheels. You've got a bunch of flywheels spinning really, really fast. Those are big, heavy objects. And if that thing breaks, it can go boom, and that has happened. However, the systems that are on the market today, the ones that we've investigated and that we're actually working with, we look at burying them, put them in a containment, a vault underground. So if something did break, then the risk is minimized. But the same kind of risk applies to pump storage. If you're, got a reservoir, you can have a burst reservoir and that can flood and cause damage. Same with compressed air systems. If they let go, that can cause damage as well. I mentioned big pump storage systems and their licensing requirements, and that's mostly around wildlife habitat impacts. That doesn't really factor in, so we're not going to get into that much in the conversation today. But, the fact is, if you have a system that requires a lot of space, then that space can't be used for something else. It's clearly an impact on the environment. So end-of-life disposal is a factor as well. Lithium batteries used to be, you really can't recycle those, but increasingly the energy storage lithium batteries are increasingly starting to be recycled. But it's tough because, that electrolyte is not easy to recycle. I don't know that much about it, but I understand it's tough with lithium batteries. But some other chemistries are more recyclable that we're looking at down the road. And just simply, end of life, the longer the life, the less overall impact the end of life disposal is going to have. So even if you do have hazardous materials coming out the end, if you've gotten 20 or 30 years out of that battery versus 10 years, it's got a lot less impact per kilowatt hour that you've been able to put through it and the amount of pollution you've been able to prevent. So you want to move to the next slide, Josh?
Yeah, the only other point I'll add here, both, comparing storage technologies to one another, but also, I guess, comparing storage technologies to fossil fuels is manufacturing or initial production. Certainly with fossil fuels, you have mining involved that has environmental impacts. And then there's relative environmental impacts between the different manufacturing processes for these different technologies. A little harder to quantify, definitely probably not something you're going to be able to get a lot of data on. It may not be necessarily part of your equation, but just another consideration.
Yeah, that's a good point. Actually, the lithium itself is kind of a rare mineral, relatively speaking, and a lot of the minerals that are used in batteries are rare, and they don't come out of the ground easy. So yeah, there's some pretty significant impacts from just obtaining those materials. You're right. Okay, so we're not going to go through every single part of this, but we just wanted to touch, briefly and point to some of the different attributes of these different storage systems, because it gets to what I was saying before about the efficiency of the system and the lifespan of the system. One thing that this table doesn't show is the degradation factor. So some systems degrade, and as a result, they have shorter lifespans. And everybody who has a laptop computer or a phone knows this from experience, that lithium batteries don't last. And the more you discharge them and the lower you discharge them, like the more, you can't discharge a lithium battery all the way down to zero charge, or you'll ruin it very quickly. For energy storage batteries, the rule is not below about 30%, depending on the type of system. So, you may have theoretically 100 kilowatt hours of capacity, but in principle, you can't actually discharge all of that. So that's, a factor just in terms of calculating your capacity and the amount of, resource that you're putting in to start with. But also, it's just how long does it last? Because if you are using that battery every day in a daily charge-discharge cycle, lithium batteries degrade fast. So like 6 to 8 years is about all you're going to be able to get out of. Okay, now, some manufacturer might argue with me about this, but generally speaking, 6 to 8 years, maybe 10, is what you're going to get out of a lithium energy storage system that you are cycling on a daily basis. So if you have a 20-year, you're planning on a project and you have a 20-year cost-benefit analysis, you have to figure on replacing those batteries in 8 or 10 years. Or you can leave them in place and just add more. You might have some capacity left. But the point is that adds up, just in terms of financial cost, but also in terms of pollution prevention. It's just all that additional lithium that's having to be mined and now is entering the environment one way or another. And what you're able to achieve with your investment in that battery. So other systems don't degrade as fast as lithium, and that's one of the reasons. Now, people are still working on lithium battery systems, trying to get them so that they don't degrade as fast, and improvements have been made there. But maybe this would be a good time. And I mentioned lead acid batteries. I guess I should just say, look at the energy density. You can see lithium batteries have a really high energy density. And that's one of the reasons, really. That's the reason that they are, well, not the only, a main reason that they are so ubiquitous today. Looking at the other systems out there, the energy densities are much lower, and those are things that are, development is continuing to advance. Even lead acid batteries, they used to be worse than they are today in terms of energy density, and so there are improvements being made there. And also, you see lead acid batteries lasting many, many years. You may not get many, many years out of your car battery, but it's a little different application than for an energy storage system. Josh, would this be a good time to turn it over to Rob and focus in on flow batteries?
Yeah, I just want to, also kind of balance the lithium ion. I think we may be shooting down people's interest in lithium ion. It's currently just the most cost-effective, most reactive source of energy, which is important too. Some of these battery or energy sources can't react to the instantaneous demand. So if you have a large facility, a gaming facility, and you turn on the HVAC system, that has a very significant draw in an instant, and lithium ion responds very well. And so, it's a market leader right now for a reason. Hopefully with development out there, there's different use cases, and the cost of other technologies will come down, and it'll be kind of a more balanced market. There's definitely been advances in ensuring that lithium ions aren't blowing up anymore. I mean, we have companies like Tesla and others, investing heavily in these things, making them as safe as possible. They're in all the cars that are driving around the roads as well. And that round trip efficiency too. It's, you're not losing energy that you are with those other ones. And they typically have a minimum of a 10-year warranty. In California, it's actually a requirement if you're getting rebate money from California for it. The industry experts or those selling lithium ions will tell you, minimum of 10 years warranted, and then, possibly up to 15 years or so as well. But, I think you got to look at the cost and the use case, and we'll talk about some examples where we're using various technologies in a moment. Yeah, let me turn it over to Rob. I'll pull up your slides, Rob, unless you want me to hand over the controls. And just to let everybody know, we have about 20 minutes left, and I can encourage people to continue to ask questions throughout, but we'll continue to kind of delve out content to provide education on this topic. Rob, I'll pull up your slides for you, unless, like I said, do you want me to hand you controls, or is this good?
This is good. Thank you, Josh. Just to piggyback on what Josh and Mike were talking about with the different technologies, we find that the best systems and the most thought out systems use multiple technologies in a single site. The weaknesses and advantages of the different technologies do work well together oftentimes. And we do work really well with the lithium system, for example, and we kind of back each other up. It's kind of cool. So really quick, and I think I'm only going to, 3 to 5 minutes worth of presentation on my side, but basically we in Invinity Energy Systems, go ahead and go to the next slide. We are the leading global manufacturer of vanadium flow batteries. Our whole business model is on modular flow batteries. In the past, flow batteries were, large projects that were custom engineered and built on site. And our whole business model and strategy is to spend an extra $10 in the factory, build a product so that you can save $1,000 in the field, and thereby making everything a little bit more streamlined. Go ahead and go to the next slide. So the way a flow battery works, just kind of in basic concept, is you have these 2 tanks of electrolyte fluid, and in our case, vanadium, an element on the periodic table, is the active ingredient, and suspended in sulfuric acid and water. It's about 70% water. This fluid is pumped through these cell stacks there at the top, and in the cell stacks, that's where we connect a couple of wires, and we either charge and put in electrons, or discharge and take them out. And that's pretty much it. It's very old technology. It's been around for several decades. And yeah, so it's a very large, heavy technology, but also very well understood and reliable. And because it's 70% water, it has no fire risk. We're more likely to put out a fire than to start one. Go ahead and go to the next slide. So the way we like to describe our technology is that, you know, every piece of machinery has a specific purpose. To Michael and Josh's point earlier, Tesla batteries, I'm sorry, not Tesla, just lithium batteries have a purpose. They have a space in the market. We like to liken lithium batteries to, say, a sports car. It's fast, it's responsive, it has a specific purpose. We, on the other hand, like to compare ourselves to more like a backhoe. They are more expensive, typically more capital expenditure than a sports car, but they're built for heavy use. They're built for consistent, constant use. And the one thing you don't want to do with a backhoe is keep it in storage, because the point of having this kind of machinery is to gain savings and or revenue, because it's out working for you and making you money. So they're both excellent pieces of machinery. They just do different jobs. And it's important to find the right technology and the right fit for the right application. I'm going to go to the next slide. So the way we fit in the market is flow batteries are best suited for long duration, high cycle applications. So we're talking anything more than 4 hours of duration. Michael made the example of maybe, you know, it has a 15-minute duration. That's not a good flow battery application. We like anything above 4 hours. Also, we like to see anything more than 300 cycles per year. Granted, a flow battery can handle less. It can handle 50 cycles per year. It'll be fine, but we find that our customers see the best economics when they get above 300 cycles per year, because there's no incremental degradation. These batteries don't degrade. They have a higher CapEx, but if you can really use them, like I said with the backhoe example, if you can use them more than 300 cycles a year, we end up having a lower total cost of ownership over the project life. And then, you know, because the battery can do anything, I like to suggest, you know, if we're going to bring a battery to the site that can run 24 hours a day, 7 days a week, what would you do with it? And most people start to get creative around what they can do to save. Maybe we are going to have some resiliency, and we're going to shave demand and do arbitrage and do multiple different services with the same piece of machinery, and stack services to multiply the revenue and multiply the savings. Something that's typically not suggested with other technologies, because other technologies tend to degrade per cycle. We don't. We recommend that people use our system just as much as possible. But more to the specific details of this conversation, when it comes to environmental advantages, to, you know, reducing pollution, a flow battery, very importantly, has no nickel or cobalt exposure. I'm not sure if anyone's really looked into that, but other technologies, especially lithium, have a lot of nickel and cobalt, which comes into environmental impacts, human impacts, a lot of really nasty stuff going on with nickel and cobalt mining. We don't have any dangerous off-gassing. There's no fire risk, like I said, and the electrolyte is not consumed. Unlike a lithium or other technology, which degrades and wears out, the electrolyte is infinitely reusable. You could essentially, at the end of the life of the system, take out the electrolyte and continue using it in a new system. The things that degrade are, you know, sheet metal and hinges and joints that will eventually need to be replaced with any piece of machinery. But most of the components of our batteries are easily recyclable, blue bin, in fact, recyclable, and very easy to take care of. On the other hand, other technologies very often have high costs to dispose of the hazardous material. Not only cost financially, but to the environment. And it's unfortunate that we don't have the regulations yet to really define what those disposals need to be. They're coming, but those regulations are still being written. Lastly, just to touch on the toxic fumes and off-gassing, not sure if anyone's aware, just this week in Livingston, out in the UK, was a new lithium fire. And one of the things that happened was the off-gassing from the fire endangered the residents nearby. That during normal operation, everything, it doesn't off-gas, but in a fire or other catastrophic situation, it becomes extremely hazardous. And it's also absolutely something to consider. So anyway, just real quick, like I said, overview about who we are, what we do. And I guess I'll turn it back over to Josh.
Thank you, Rob. I appreciate it. And so Rob's contact is here. Rob, I see you have some examples too. I was planning on posting these on the TribalP2Action website. Do you want me to post it with the case study examples as well, so people can see some of the work you guys have done?
That was more for an appendix in case we needed it, but I don't see any problem with posting it.
Okay, well, feel free to circle back if you want me to, have a certain slide deck posted online. But thank you, really appreciate it. And we'll actually, in just a moment, kind of talk about a use case that we're working with Rob and Invinity on for one of the tribes we're working with. So real quick, I'm not gonna go through this slide deck. Another group that we're working with is called Amber Kinetics on one of the same project actually, and they manufacture flywheel energy storage systems. And I'm not going to speak to it too much just because I'm not an expert in it. But this is some of the benefits that are kind of along the same lines in terms of both economics, environmental, and safety. They don't degrade in capacity, unlike lithium ion. There are no daily cycling limitations similar to flow batteries. It's non-flammable, so there's not a safety risk from that. Certainly, there have been instances of flywheels going off track and flying up in the air and destroying everything in their path. But, there's ways to mitigate that in terms of location and things like putting in the ground, which is the approach Amber Kinetics has taken, and a relatively high round trip efficiency as well. And then on this, as a slide notes, 100% recyclable. We're not talking about that this isn't a chemistry, it's metal. Probably, lubricants perhaps are need to be considered for this. Maybe not. But I'll show you what it looks like. That's kind of not an exact, but this is kind of a cutout of what it's really just a container with a large piece of metal inside that they use energy to get spinning, and then when they want energy, they kind of basically extract energy from the friction from it. And I'll post these slides online as well, so you can learn a bit more. But so you can get a sense too of the size and how this is going to be installed in the project we're working on. They dig a hole in the ground to reinforce it, and they put how many of these units in there and connect it to a load, a facility that needs this energy. And here's an aerial site, another example, single system, and then in this case, in installation they have in Hawaii, where it's actually being paired to store solar energy. And you'll be able to contact Amber Kinetics and Ed Chow directly with his contact information here. Okay. So I just want to, as we wrap up here, well, let me pause for a moment here and just ensure that people have taken a breath and making sure we're checking in and see if there are any questions. Any questions on any of the technologies we've gone over before we get into a few further case studies on some applications in tribal communities that we're working with?
This is Sherry. I was just wondering about the examples of where the vanadium batteries fit well, where they're a good option.
Yeah, great question, Sherry. The best fit is when you can use the batteries on a daily or multiple times a day application. So for example, if you were able to get information around the load or other, what you're looking to do at the site. Maybe I can do it this way. Here's an example. I was working with a mining facility. They had a very interesting load pattern where they wanted to do some peak shaving, but they also wanted to offset afternoon peak rates and then charge at night and discharge in the morning. And in so doing, they were able to fully charge and fully discharge the battery a full 2 times every single day, giving them about 600 cycles a year. With that project, they paired it with solar They had some great economics, great performance. Essentially, like I said before, the 300 cycles per year is kind of the line in the sand that we typically see is a good fit. If you'd like help, I'm sure Josh and Michael would be more than happy to walk you through kind of the different applications and options around what might be done at your specific site.
Well, just
Yeah,
one
no,
other question. I mean, are we talking industrial? Is this the usual?
Oh, thank you. Yes. So our products are geared toward commercial, industrial, small utility, and moving forward, as a company, we're moving toward larger utility. Currently our largest project size is about 8 megawatt hours. And we're in negotiation with projects that are in the triple digit megawatt hours. So, you know, at the very smallest, something that can hold a 20-foot container. At the very largest, something that's many miles square.
what's the use case for the 20-foot container? Like, what's the optimal, just a commercial building or a series of commercial buildings? What type of load are you kind of economically serving well at the smallest capacity?
The smallest, so just because it's top of mind right now, I'm working with a church in Southern California. They want to buy our smallest unit, which is a 20-foot container, to offset demand and do arbitrage. Likewise, we could do something similar for an industrial facility. It just depends. But yeah, small commercial is probably the smallest that we would go.
Okay, thanks, Rob.
Good
Any
question.
more questions, Sherry?
No, that was helpful. Thank you.
Yeah, and I think, I'll just kind of elaborate on what Rob muted myself. If you look back at this chart, you see, you talked about 600 cycles in a year at that mine. You look at lithium ion, that battery is going to degrade really fast. So lithium ion would not necessarily be the best use case for that. On the flip side, let me kind of fast forward a little bit to the project working on that actually includes lithium ion, flow batteries, and flywheel batteries in pretty significant amounts. We're using this combination because we're balancing kind of the benefits and what each system does well versus what lithium. So lithium ion is really good in short bursts. It's going to this is for a casino project, and this casino experiences those PSPS outages on now a regular basis, where they're having to shut down because they're losing power for a day plus. And so they need the capacity to be able to be self-sustaining, stay online when the power goes out. The flow and flywheel batteries are kind of storing a significant amount of storage that will keep them operational for an extended period of time, a day or more, in addition to providing the ongoing economic benefits through energy arbitrage and peak shaving. But what they can't really do as well is when the power goes out, they don't necessarily have the instantaneous capacity to transition into an off-grid mode. I think the technology is emerging. Flow could support it if it happens to be flowing at that moment the power goes out. Flywheel has instantaneous capabilities, but they don't have the technology right now to, the power goes out, that your power will stay on by switching over to flywheel. Lithium ion, on the other hand, has that instantaneous power and the controls capacity available right now. So the lithium ions in this current project are the primary purpose is to allow that bridging so that there's a seamless transition from on-grid to off-grid when the power goes out. So they're not shutting down and doing a black start. They're not turning off slot machines. They're not turning off the HVAC system. So we're kind of sizing it where it's a 15-minute lithium ion battery that can handle a huge load at once, and then allow the flywheel and flow batteries to kick back on for that ongoing outage capacity that's going to get us through a day or more, that can store that solar energy that's being added on site as well. So this is kind of one use case scenario with a combination of energy storage technologies. I also want to point out that we've talked about a few different complex systems. You can get down to a very simple solar plus storage system. This is a tribal fire station project we're working on, and we got some grant funding for which we did for that other project as well. And in this case, we're just adding some solar, we're adding some battery storage. They already have a diesel generator. So we're combining all those, and it's a, kind of a relatively simple, straightforward system. It's going to provide this, it's going to do 100% net zero energy, just like San Pasqual being offset by solar. And so it's going to give them savings on an ongoing daily basis. But then when the power goes down, they have a large battery, a 4-hour battery, actually, that's going to allow them to sustain that energy, continue to use that solar when the grid goes down. And then if that power runs out from the solar and the storage, they then can switch over to the diesel generator to continue operating as a last resort. But they have redundancy so that, when the battery does run out, or if it does run out, they're not turning the power off at that point. And then, kind of the last example is another tribal project, casino project we were doing some investigations into. And the only reason we included this one as well is that this one actually included thermal energy storage too. So not only having a lithium-ion battery plus solar plus backup generators, but pairing it with thermal energy storage, which has two purposes as well. Cost-saving purpose, if you have a thermal load that you can deploy to reduce your HVAC load, that's going to save you money. But at the same time, when the power goes out, it's usually hot. It's usually as a result of wildfires or heat. Then that thermal capacity is going to reduce that HVAC demand during the outage, which is going to reduce your energy electricity needs as well during that time period too. To kind of wrap up, and I'll let Michael share anything as well, but there's some various tools you can use and resources you can go to analyze these projects. Some of them are free, some of them you have to pay for. Lawrence Berkeley Labs tool and NREL's system advisor model. I've used Homer, I've used Energy Toolbase. I have not used the other tools necessarily. And then EPA has an electricity storage website you can go to. And then there is a global energy storage database hosted by the Department of Energy, Sandia National Laboratory. Michael, do you have anything to share as well as we wrap up?
There's many things I could say. Well, one thing I wanted to point out is that a microgrid doesn't have to have energy storage in it. Most of them nowadays do. The most cost-effective microgrids we've seen are the ones that use a minimal amount of energy storage, at least if we're only talking about lithium batteries. So we've seen, a lot of the microgrids that we've been speccing out for people only have about 15 minutes of battery storage capacity because it's expensive. The amount of power it can deliver in one moment, that's cheap. The amount of duration it can deliver it for is expensive. That's where the actual storage capacity, really gets big. So that's one of the reasons that we're looking for alternatives to lithium batteries and trying to find systems that have better long duration characteristics like the flow batteries and like some of the other systems do. So I just wanted to clarify, not all microgrids have storage, and we're trying to work on, trying to find more cost-effective long duration storage systems.
Yeah, the projects we're working on are all federally and state funded, or a combination of one or both. And so we're going to be doing additional presentations on these projects as they progress. And part of it is the California Energy Commission in particular was interested in funding those non-lithium ion storage technologies, the flywheel and flow battery, because they want it studied. They want these results to be shown and demonstrated and presented to others. So you can certainly follow us through our various websites to learn more as we progress with these projects. So as a reminder, we're wrapping up this online series. The final installation is going to be next Tuesday, focusing on pollution prevention, implementation, and training, kind of tying it all together. How do we move forward once we've done all of our assessment and planning type activities? How do we actually start realizing the environmental and cost savings? That'll be at 10 a.m. Pacific on Tuesday, and you can go to the TribalP2Action website to register for that. And with that, I really want to thank you all for coming and joining us today, and sharing your questions, your challenges, and hopefully you learned a bit of valuable information that will help you in planning for your projects. So thank you very much. I want to thank Rob for joining us today, Michael Bird, John Flores for sharing his experience with San Pasqual, and Jessica and the EPA for supporting us, and everybody for joining us. So thank you very much, and we look forward to hopefully seeing you next Tuesday.